Okay, another information that I use that I changed the slide for this back steady state lecture because I found out that there is a graphical error in the design of the MOSFET. Okay, this the MOSFET, the N-channel MOSFET has the arrow that enters the device, like this one. Okay, while in the other set of slides, the arrow points, say, up, so exit from the device. This is the symbol from the PMOS. Okay. Sorry about that. It happens when you use cut and paste, and the error was, say, at the beginning, and you can have all the symbols that are wrong. Okay, but pay attention. And MOSFET as the power MOSFET symbol as the arrow that enters the device. Okay, quite different from the analog symbol of the MOSFET of the N-channel MOSFET, in which the arrow exits. Okay, so take note, pay attention about this fact. So I reload all the slides with this symbol modified. No changes in what is written under the feed. Okay, no problem. Okay, what will just let me summarize what we did in the two previous lectures. Okay, we start talking about the buck, which is one of the fundamental topology of switch mode power supplies. We started to talk about the CCM operation mode of the buck converter. We derived a value for the inductance L, which makes possible for us to operate in CCM. Okay, remember L higher than a certain expression, okay, which involves the duty cycle, the load resistance in the switching frequency. Then we learned something about real components. Okay, real components have always some additional, say, parasitics elements for free. Okay, inductance maybe most of the time are, say, described in terms of a series of inductor and a resistance. Capacitance depends on the kind of capacitors you are using. Electrolytic capacitors, they are described by a series of capacitance, an inductance, and a resistance. Ceramic capacitance have no the equivalency resistance. Okay? On the basis of this fact, we have to understand that some of the devices, for example, say MOSFET, that can be described in terms of resistance, have conduction loss, so conduction losses that you can have when the MOSFET is on, that are better described with the root mean square value. And this happens anytime you have components that has some parasitic resistance on them. Okay, for example, capacitors. Okay, if you have capacitors like the electrolytic capacitors, and then you have a resistance which is equivalent to resistance in series, then in that situation, the root mean square current through a capacitor is an important parameter because from this parameter it depends the, say, dissipation of power, also in capacitors. Okay, and that leads to, say, overheating the components and to shorten the life of the other devices like the switch, like diodes or bipolar transistor or IGBTs, they have own conduction that does not depend on resistance. Okay, they are just more or less, it can be approximated by a constant voltage. So in that situation, the dissipation is better described by the average current. So for the diode, for the, say, bipolar transistor, IGBTs, we are searching for the average current as dissipation parameter. Then we learned something about the switching dissipation, which of course anytime you turn on and off the devices, which depends on the frequency. And then we started to describe the all the waveforms that you can have in the buck converter. Okay, let me share the widescreen in order to continue this discussion. Okay, we have our buck, which is described in this way. Do not forget the input capacitance cross B in and the output capacitance V naught across V out, or V naught, L, diode, and switch. Okay. We derive the expression of the current through the inductor, and this current is the first one we discussed. Because from this current we can understand if the device works in CCM or DCM. Okay? So since we are talking about CCM, the current in the inductor is always positive, like this one. The behavior is periodic with period Ts. We can call this first part as T1 or T-on. Okay. In this section from 0 to T-on, the switch is on, while from T-on to Ts, the switch is off. And then we derive, for example, the current through the diode, and the current through the diode, okay, is the current flowing through the inductor when the switch is off. So the current through the diode is simply current here, okay, the yellow one. And then we also have the current through the MOSFET, so through the switch, which is the current of the inductor when the inductor is on. So when the switch is on. So here. Okay. Let me discuss what we evaluate as a last topic, the last lecture. So the switch current, this one. Okay, the switch current is the current flowing through the MOSFET, because we use typically modern power supply from say less than 1 kilowatt of output power. The MOSFET are the transistors that you can use. They are faster than other devices, so typically you can use any MOSFET. Okay? We know that the average current flowing through the inductor current is the same of the I naught current, so the current flowing to the load. If you have the same level here, if you get the same level in the switch current, this is the I naught current. Okay. Then you have that this current is the minimum current here. Then you can have also the I maximum current, which is the peak value of the current. Okay. If you use MOSFET as a switch, then you have to evaluate the root mean square current flowing to the MOSFET, because it, from this current depends the conduction loss. Okay. Of course, there exists some very accurate expression. Okay, I adopted an approximation which is called the flat top approximation. In this approximation, I can modify the current through the switch by flattening it as the value which is I0. Okay? This is now I0. So this level here. So the current is no more a trapezoidal kind of current, is something that is similar to a rectangular wave. Okay? Like this way. So now from this current, I can evaluate the root mean square in a simplified way. And in order to get the root mean square current of this rectangular way, I have to say square it. And so let me evaluate the square of this current. This current is I naught square during T on, 0 for the remaining part of the period. Okay. Then I get the average of this current through the period. In order to get the average, I have to simply consider which is the area here, and the area is I naught square multiplied T on. Okay, and then I get the mean value. Okay, so root mean value over Ts. That is also I naught square multiplied D, the duty cycle, because D is the duty cycle. Okay, and this is I switch root mean square value, and then you have to root it. Is I naught multiplied square. Of course, this is an approximation because of the flat top approximation. Okay, so this is the root mean square value of the current through the switch that we should use when we want to compute the conduction loss of this MOSFET. Okay? Of course, when you want to get the maximum, you have to insert here the maximum duty cycle, and then you get here the maximum current, okay, in order to get the maximum possible value in the worst case. Another parameter that we have to consider in order to buy the MOSFET that you can use in this buck converter is the maximum voltage that the transistor can have across this drain to source terminal when it is open. Okay? When the switch is open, the voltage that you can have across it from the drain to the source is simply the input voltage, okay? Because when the switch is open, the diode is on, okay? So the red arrow here, this voltage, is exactly the voltage at the input Vin. So the V switch maximum is exactly V in. Okay, of course, V in maximum if you can search that worst case. This voltage here is important in order to buy the MOSFET because the MOSFETs they are built with different breakdown voltages. Okay, so of course you have to choose the breakdown voltage of the MOSFET to be a little bit higher than the maximum switch voltage. Okay, so the breakdown voltage of the MOSFET typically is indicated with these ladders. Okay, breakdown voltage from the drain to source when the gate is shorted. This is the typical datasheet manufacturer's indication. Okay, this should be higher than the switch maximum in order to be sure that for the operating points of the converter, this MOSFET is always cannot have some malfunction due to the fact that it can go into the breakdown region. Okay? So the breakdown region of the MOSFET should be higher than this one. Another consideration that we can have in this waveform is to compute the average current. The average current through the switch. This average current can be derived by using this waveform, the rectangular waveform, which comes from an approximation, the flat top approximation. And this, or maybe is, you can also evaluate it by the direct waveform, and you can have the same result. Let me get the average value of the switch by using the original and not modified, not approximated way. Okay, so now the average value is this one. Okay. The average value is simply the area of this trapezoid over the period Ts. How can you get the area of this trapezoid? You have to get the summation over this segment plus this one then you have to divide by 2, and then you have to multiply it by the height. So the average value is simply I minimum plus I maximum divided by 2 multiply TS divided by, sorry, divided by TS and multiplied by TO. I minimum plus I maximum divided by 2, this is exactly I naught. So this is I naught and this is the duty cycle. Okay, so the switch average current is provided by this expression. Okay. So you can get the same results if you can use the flat top approximated waveform, or you can have this exact expression of the current. Okay. Why we use, I derive this average current through the switch? Because I said before that the average current through the MOSFET is not important to get, say, information about the conduction loss. Typically, in exercise, when you are, say, are in the first design of your converters and the buck converter, this information can be useful to check if my calculations are correct. Okay, I know now that the switch current is I naught multiplied the duty cycle. Okay, but this average current flowing to the switch here is also the current flowing through the source, is the I in, because no DC current can flow to the capacitor in steady state due to the charge balance characteristic of capacitors. So all the DC component of the switch current, so this component here, is the input current, the DC input current. So we can say that the input current is exactly I naught multiplied by D. So with this information that I report again here, I naught multiplied D, let me consider the input power imputation. Input power is V in multiplied I in. So it's V in, and I in is simply this expression here. So I naught multiplied D. Remember now that we have a conversion ratio that for the CCM is V naught over V in, which is the duty cycle. So V in multiplied the duty cycle is also V naught. So we have V naught multiplied I naught. But this is the expression of the V naught. So we get that the input power is the same of the output power, and this is exact for my circuits in which I have no resistive component. All the components are ideal, okay? And so I'm expecting that there will be no losses inside, okay? And so for that ideal situation, the input power should be the same of the output power, so the efficiency is 100%. And so I can say get this kind of result as check the check of my computation. Okay. I just computed the root mean square value of the switch current. Okay. Let me focus now on the input capacitor current. Okay. So input capacitor current. Let me redraw the circuits. This is the switch, and then you have here switch current. Here you have this current, which is the current through the input capacitance. Here you have the DC input voltage. And here you have the input current. This node is the node that I call active node. And so we have the Kirchhoff current law. I can say that IC in B is equal to I switch minus I. Okay, this is the Kirchhoff current law for instantaneous value. Remember that in order to get IC in, we have to make this difference, okay? Okay, so I have I switch. Let me withdraw again the switch current. I have some problem in using the whiteboard. Sorry about that, but I don't know what happens sometimes. So please be patient if you see some say extra line like this one. Okay, so this is the switch current. I try to be more precise as possible. Yes. One here. This is the switch. And this is the current that I have to draw, which is the current IC. Okay? I just said that the input current is just the average value of the switch current. So we can say that switch minus E switch. Okay. Remember that sometimes the average value is indicated by, let's say, the typical symbol, which is this one with a bar over it, or let's say the capital I. The same. So I switch minus the average value, which is something like this. So the input capacitor current is something like this. It has no DC value, okay? This means that this area, the positive area, is the same as the negative area. Maybe the drawing is not exact in this sense, but the objective understand this. Okay. We get a similar construction for the output nodes for the capacitors. Output capacitor. Now we get this instantaneous value of the current flowing to the input capacitor, but remember that we also want to know the root mean square value of this current, because typically capacitors that you can have at in are electrolytic capacitors, and so we have to know the root mean square value to understand, say, as a parameter to use for choosing this capacitor. So, goal now is to compute the root mean square value. In order to get the root mean square value, we can use the Kirchhoff law for the root mean square current. So, can we write that the root mean square current of C in is equal to the difference between the root mean square current of the switch and the root mean square value of the input current? No, this is not possible, okay? You just can't use the Kirchhoff current law for average value of the current or instantaneous value of the current, not for the root mean square. But we know that exists the quadratic Kirchhoff current law that says that anytime you have a current, which is the summation of an AC plus a DC component, say I AC plus DC root mean square value square, this is equal This is equal to the ISC root mean square value of the current plus IDC. Okay, so I have to solve this problem because it's not possible for me to write and it's not possible for you to follow me. Okay. So this is the Kirchhoff current law. Now let me check if at node A there is a situation which is similar to this one. I have the switch current here, which is a current that has simultaneously a AC and DC part. Okay, you can see in the yellow part, yellow graph here, that this current has an AC part or a variable contribution, and then I have an average value, which is I switch. So it has both AC plus DC. Then I have a current through the input capacitance, which is just AC, because no DC contribution. And then I have a current, which is C in, which is just DC. So we can write, you can use the Kirchhoff quadratic, the so-called Kirchhoff quadratic Kirchhoff current law for this node A. And in that way, we can say that IC in root mean square value is equal to what? To the switch current root mean square value square minus the DC part. Now we know that I in is equal to I naught multiplied D, because we just derived before. Okay. And then we also know that the switch root mean square current is I naught square multiplied. So we can have that this is I naught square D minus. Okay. So the in root mean square value is I naught D minus D square. So it depends on the output current and depends on the square root of the duty cycle minus square value of this duty cycle. Let me share with you the plot that is indicated in this slide, which is exactly the expression of the root mean square value of the input current divided by I naught. Okay, so supposing that I naught is constant. So the root square of D minus D square. As you can see here, from D that ranges from 0 to 1, you get this behavior, okay, of this function that as a maximum. Okay, and so in order to have the worst case possible situation, okay, you have to get the maximum at D 0.5. And when you have D 0.5, this root square becomes 1f. And so the maximum possible root mean square value of the input capacitor is 1f when duty cycle is 0.5. Okay? Of course, if your operation does not include 0.5 as a duty cycle, for example, your duty cycle just ranges from 0.6 to 0.8, you have to understand that you have to put the maximum duty cycle, sorry, the minimum duty cycle 0.6 here, so you can get the bias there. Okay? anytime the 0.5 is included in your working operation condition, for example, when the cycle ranges from 0.3 to 0.6, the maximum is at 0.5. We also have to understand that there is a very little variation in this, say, area here, okay, that is between 0.3 to 0.7. Okay? It's almost flat in this part. Okay, so there is no so huge variation for the different duty cycle. Okay, but in any case, you have to consider the worst case situation, and this happens when the cycle is 0.5 and it becomes half the output current. So let me again share the screen in order to look at the diode current. So the diode current is the current flowing through the diode, and so is the inductor current when the MOSFET is off. So the diode current is something like this. So this is yes, and this is the on. This value is I minimum, then we have I maximum here. Remember that I naught is I minimum plus I maximum divided by 2. So the I naught current is something that is here, in between, exactly in between, the midway between I minimum and I maximum. What is important for the diode? For the diode is important in order to compute the conduction loss, the average current, okay? Because when it is on, it almost constant voltage, okay? The voltage drop across the diode. So, which is the average value across the diode, ID, is given again by computing this area, the area under this trapezoid, and averaging it over the TS period. Again, we have to get the area of this trapezoid, so I minimum plus I maximum divided 2, multiply the 8, which is now Ts minus Tion, divided Ts. I minimum plus I maximum divided by 2 is I naught. Ts minus Tion divided Ts is 1 minus 2. And so this is very important parameter for my direct average current. Of course, if you want to search for the worst case situation, you have to insert here the minimum cycle, and you have to get here the maximum current. Okay. The maximum current, it happens when the load resistance is the minimum. So I mean, another parameter that can be important is also Imax for the current, okay, which is already computed for the inductance in previous slide. Average current, but another important parameter, same as happens for the MOSFET. Okay. When the diode is off, we have to understand which is the maximum voltage across the diode before it enters the breakdown bridge. And this can be easily looked at this back circuit here. When the switch is on, so it's closed, the diode is off, so it's open, and when the diode is off, the voltage across this diode, so we can say the voltage that you can have in this way, for example, from the cathode to the anode, is exactly the in. And this is the reverse voltage the diode can have across it when it is open. The maximum reverse voltage is the maximum input voltage. So you have to choose a diode that has a breakdown voltage which is higher than the maximum input voltage. Okay? So let me write this one. The maximum reverse voltage, so from the cathode to the anode, is the input voltage maximum. So the breakdown voltage of the diode should be higher than Vmax. Okay, so from this information you can understand which kind of diode. So let me discuss now a very important thing about the computers. Okay, up to now we get I employed from this discussion the small ripple approximation. Remember what is the small ripple approximation? The small ripple approximation states that for this first order analysis of the Bach operation, and this happens also for all other topologies, we can consider the output voltage to be, let's say, exactly constant at the value V naught that I want you to consider. Okay? For the small ripple approximation, the output voltage is not dependent on time. This is constant. It's constant to the value V naught. This never happens, as I already said at the beginning of this lecture, because the filtering action of inductance and the C0 capacitance is not perfect. Always you have at the output some residual components at high frequency, the switching frequency, and all the harmonics. So what happens is that typically you have to consider, which is this ripple in your design, at the point that as a specification always you can have that delta V naught is less than some maximum value. Typically this is say a few percent of the V naught average value. Okay, so a few percent of V naught. So for example, if you want to design a buck converter to get 12 volt at the output, okay, delta Vmax can be, say, 1% of 12 volt, 10 millivolt. Something. Why you get this ripple, okay, which has been, say, neglected in my previous analysis? Let me focus the attention about this kind of situation. So for a few next moments, next description, we can get rid of the small ripple approximation to consider what happens in practice with the output voltage. Okay? So let's consider the inductor current. The inductor here, the capacitor here, this is the C0, this is the node I call out. Then we have a load. Okay, this is the output side of my converter. This is IL, I0, I0. So IL is this one. This is the period Ts. The current through the output capacitor, I C naught, is simply the inductor current minus its average current, and the average current is so it's something like this. Remember that I call the peak-to-peak variation this inductor current as delta IL, the ripple inductor current. So the ripple of inductor current is also the peak-to-peak variation, the current through the capacitor. So I have a capacitance that has this current behavior, this current waveform. Okay? But also you should remember that for a capacitance, the following relationship holds between the voltage and the current of the capacitance. Okay? Also, you have to consider that the voltage across the capacitance, VC naught, is the same of the output voltage. Okay? This is the reason why I put here V naught and non VC naught, because they are the same. So what does it mean? That if you look at this current behavior, now we can evaluate the expression of V naught. Look at this point here, 1, 2, 3, anytime the current crosses the zero. Okay, when the current is zero, it means that if you look at this expression here, if the current is zero, it means that the variation of the voltage, the output voltage, is null. So it means that in this specific point here, we have no variation versus time. Okay, the rate of change of the output voltage is null. So we can say that here you have something that has a slope which is horizontal slope. This point. Then look at this part of the current here, okay? This one. The current is negative. So what does it mean the current is negative looking at this expression? That the rate of change of the voltage is, let's say, negative. Okay? So the V naught over the V is negative. So it means that for this region here, the output voltage has a negative slope. In this interval here, which the current is positive, the variation of the voltage versus time is positive. Okay? So it should not be surprising that the output voltage has a behavior that is, let's say, something like this. Okay? In this region, the first one, the green one here, as you can see, the output voltage has a variation which is negative. Okay? If you get a slope at any point here, you get negative slope. From this region here, which the current is positive, you get always positive slope. At this point in which the current is zero, the slope is null, so it changes the slope. Okay, so you have a variation which is something like this. Just simply analyzing the fundamental relationship between voltage and current and capacity. So, since this is the waveform that I can have here, I can say that the peak-to-peak value here of the output voltage is exactly delta V naught. Of course, this variation is obtained across an average value, which is V naught DC value. Okay? And in this case, I exaggerated a little bit the V naught voltage, just to, let's say, highlight this behavior. But now we have a means to compute this delta V naught, okay? Because we know that the variation of the current here induces a variation in the charge. Okay, so we have a delta Q, which is C naught, and this variation of the charge generates a variation in the voltage, and which is this delta Q variation. But if you look at the area under this current here, that is from here to here, okay, this variation of the charge, which is positive, induces a delta V from this point, from the minimum point, to the maximum point. So this area here is delta Q. Okay? The area under the current curve versus time is always a charge. Delta Q can be computed because it is an area of a triangle. Let me highlight this faster current here. I see versus time. So I'm computing this charge here. So in order to compute this area, I need the 8 of this triangle, and the 8 is delta IL over Q, because delta IL is the peak-to-peak value. Okay, and since we have no DC component, the peak value is delta IL value, and I need the base of this triangle. But the base of this triangle is exactly ds divided by 2. Is alpha period. Okay, ds is the interval that we have here. The positive part is exactly half the period, because there is no DC current. Okay, so in this condition is happens. So 1/2 of the 8 multiplied the base. So this is delta IL over 8Fs. This is the variation of the charge, which is also equal to C naught. So from this expression, you can say that delta V naught of the ripple, peak-to-peak ripple of the output voltage, is delta IL over 8 C naught. Look at this expression here. This expression has a voltage ripple at the output, delta V naught, which is the peak-to-peak variation of this voltage here, okay, which depends on the peak-to-peak value of the inductor current ripple. And this is the reason why in a good design, delta IL is always kept to a minimum value, 2% of the I naught current. Remember my previous assumption that I not fully justified at that time. Okay, I said pay attention that delta IL is well less than I naught. Okay, for example, I use this approximation to derive the root mean square value of the inductor current. Okay? Now it can be fully justified. If you want to cap at the minimum the ripple of the output voltage, you have to cap minimum this delta L. Okay? Then delta L is, say, should be designed to be 3% of I naught in order to cap at the minimum the maximum value of the current, the minimum value of the current, so you get less stresses for all other components of the back. Okay? But one other good reason is to cap at the minimum the output voltage. Then it depends on the switching frequency. So increasing the switching frequency, you can get lower output ripple, and it depends on C naught. you can use this expression to derive C naught. C naught is delta IL divided 8 delta V naught. So if in your design delta V naught is defined, 3% of the voltage you want to get, I don't know, 50 millivolts, and you know the frequency because you choose at the beginning of your design, and you get delta L. Remember that delta L is something that depends on the output voltage, 1 minus duty cycle divided, etc. Then you can get CO, C naught. Okay, C naught should be larger than this. You know, the value that I'm using, the standard value, should be higher than the by this expression to get delta V naught less than that voltage to specify. This is not completely true. Okay? What I said to you is exact, and so you can get exactly this output capacitance value depending on the voltage that you can have as a specification. It's correct. But this is perfectly true only if you have ceramic capacitors. Ceramic capacitors. If you have ceramic capacitors, then you should remember that you do not have any equivalent series resistance. Okay? And so the output capacitor is almost a very good capacitance. It's quite an ideal capacitance, okay? Except for a small equivalent series inductance that now is not considered in this analysis. Then ceramic capacitors act exactly in this way. And if you have ceramic capacitor, the output ripple has exactly this waveform here, something that an oscillation at the frequency Ts superimposed onto the average value, you know. And so you can quite recognize that if you have an output voltage that has this behavior, then you have an output capacitor which is a ceramic capacitor. But what happens if instead of having a ceramic capacitor, you have a electrolytic capacitor? For electrolytic capacitors, then you have the ESR. So we can say that more or less you have this behavior. Okay. So in that kind of situation, which is the situation you can have most often at the time, the output voltage has a different waveform. The current through the capacitor is always the same, something like this. No DC value, just the AC part of the inductor current, like this. And the output current, sorry, the output voltage has the DC value, which is V naught. Superimposed onto this average value, it has something which is so it has a behavior, okay, which more or less has the waveform of the current ripple. Okay, is again a triangular waveform. Why, of course, this kind of waveform here? Because of the ESR. Okay, is the current flowing through this resistance that, and current is the not current, that generate this kind of AC contribution. Okay, for the switching frequency, for the frequency of this ripple, okay, it occurs at frequency Ts, switching frequency Ts. The capacitor is, let's say, acts like a very small impedance or like a short circuit, and so all the AC variation is due to the equivalent series resistance. So this is why we get this kind of output ripple, which is a triangular wave. So in that situation, the electrolytic capacitance, delta VO, is delta IL multiplied ES. And if you measure with a scope, for example, the output voltage and the ripple has this triangular behavior, then you would be quite sure that your output capacitor has a large ESR. And this most of the time happens when you have electrolytic capacitor. Okay? So look at this Q expression. It occurs for two different kinds of capacitors. Okay? What happens to the output capacitance value in this case? I have to say that this is not so important. Okay? While the output capacitance value C naught can be designed for ceramic capacitors according to the value of delta V naught you can have from the specification. For electrolytic capacitance, what is important is the value of ESR. And so from this expression, you have to find the ESR you can admit in your output electrolytic capacitance. ESR is delta VO, which is provided by your specifications, divided delta EL. Okay? So when you get this value of ESR, then you can choose the capacitors, the value of the capacitor from data sheets. Typically, what happens is that in data sheet you can have capacitors that are listed for the values, but they can also have the ESR indicated. Okay, so you choose for the ESR instead of the capacitance value. If you choose for the ESRs, okay, the capacitance that can have that ESR is good for you. Okay, typically this is what happens. Okay, so you have to choose the ESRs, not the output capacitance when you have electrolytic capacity, output capacity. You have questions about this discussion. Okay, Friday at 10 a.m. when you have, let's say, the exercitation, then you can use this consideration to design a buck. Okay, so you can have numbers put on them, and then you can exercise your knowledge about this. In these two slides are summarized what we get for all the components. Okay, so look at the expressions that you can have here for the root mean square value of the currents when you need for them, the average value, the peak value of the current, the voltage across them, etc., etc. This is all the expression that I derived. So just a few considerations for the bar. The first one is that up to now we use the common rail, the negative common rail of the input voltage of this node here as a reference. Okay? This is the buck converter for the negative common rail. What happens here is that there are typically the drawback of this topology, if you want, that uses the negative side of V in as negative common rail for all the voltages, is that we have to use a switch which is an I-side switch. Remember that an I-side switch is a switch which is not directly connected to the common rail. Okay? The source of this switch is connected to this node here, which is not fixed in voltage. It can change. When the diode is on, it is the negative common rail, but when the diode is off, this node rise up to the input voltage. So the I-side switches require specific driver to operate them, to make works with not and with not. Typically, they are say expensive with respect to the low side switch. So someone decided to modify the buck converter topology, which is the first one in this slide, in order to use low side switches. Okay, so for example, let's have a look to this second slide here. Second slide, I move the switch here to this new position here. And in this position here, now the source is connected to the reference voltage, the common ray, the negative common ray. So this is a low side switch. It requires low side gate driver, which are simple. They are, say, we have a lot of choices in the data sheet. They are less expensive, etc., etc. This topology here, in which just remove the MOSFET from the positive common ray to the negative common ray, works exactly as intended. Okay, no variation of the duration with respect I described in the previous slides. Okay, so they work exactly in the same way. The problem is that if you have the load here and you need to have the load connected to ground, in this configuration it's not possible to have the load connected to ground. Sometimes you have by specification that your output voltage should be provided to a load which has some node that must be connected to the ground. In this configuration, this is not possible. As you can see here, when the switch is on, so it acts as like a short circuit, then the load is connected to ground. But when the switch is off and the diode is on, the input, the same terminal of the load that previously was connected to ground, now is connected to Vin. Okay, it's connected to Vin here. So this node, the node here, changes the voltage from 0 to Vin during the, say, the period Ts. Since we have a capacitor, the capacitor holds the output voltage V on, it happens that also this node here, the other terminal of the load, changes the voltage depending on the switch status from V0 to V0 plus V in. The difference is always V0. This is held to V0 by the output capacitors, okay, which they hold the voltage across it to the voltage V0. But what happens is that these two nodes are floating. They move their value in each period. And so this means that you can have several problems due to the electromagnetic compatibility, for example. Okay? You have what is called a common voltage here. These two node voltage changes, so you have a dV on the T. And this means that if you have some parasitic capacitance that you can have to these nodes here, for example, to other metallic plates or metallic case of your switch mode converter, then you are exciting parasitic capacitance between these two nodes and other, say, plates, metallic plates in the surrounding environment. So this is not exactly a very good situation. Okay, the operation is always the same, but in terms of electromagnetic compatibility, you can have some problems, and then if you need a load that requires a terminal to be permanently connected to ground, this is not a good solution. So what you can do if you want to use a low side switch, okay, what you can do is to move also the inductor in the negative ray. Okay, so in that situation you have your inductor which has a positive common ray. Okay, my common rail here for the load now is the positive one. Okay, so the situation is the same as before. Okay, all the voltages should be referred to this positive common ray. The operation is like the same as before, nothing changes, and you also solve the problem about the common voltage at the output, because this node here is at a constant voltage. Okay. Okay. So in this situation, you have no more common voltage problems, etc. So you can also use the buck converter with this positive common ray if you want to use a low side switch. Okay, this can be used. Another discussion that we can have is about the diode that you put here. Okay, remember that in my classic topology of buck converter, here you can have a diode. Okay, the diode is useful because it can conduct the current of the inductor L when the switch is off. Okay, it works as a freewheeling diode. Okay, it makes possible to continue conduction of the current through the inductor. Okay, remember that inductor and the current should want to continue to flow even when you interrupt it. Okay, so this is the reason why you need the diode. But there are several situations in which the presence of a diode in the buck converter is detrimental for your good operation. Just an example, which is important nowadays, is that look at what happens when you use a buck converter to generate the power supply voltages of a microprocessor. Okay, nowadays microprocessor can work for voltages that are in the range of 1 volt or even less. Okay? So you can have V naught, which is 1 volt, for example, and the current can be quite huge because depending on the operation inside the microprocessor, so depending on the dynamic situation you can have, you sometimes you have to manage hundreds of ampere with the microprocessor for a very short time, but then you can have this huge current. So look at what happens if you have P naught, which is very low, let's say 1 volt, and you have a diode here as a freewheeling diode, like in the classical topology of the buck converter. What happens? Suppose that you use a Schottky diode. Okay, Schottky diode can have, let's say, 0.5 of voltage drop. You have a 0.5 voltage drop just across the diode when the diode conducts, and then you can generate 1 volt at the output. This means that your efficiency is very low, less than 50%. Okay, because just 1/2 of the voltage is, let's say, lost here in the diode. So the typical voltage drop, even you are using a Schottky diode with 0.5 volt, is totally detrimental for the operation of the converter that has to generate a very low output voltage. So in that specific situation, in which the not as a voltage, which is comparable with the voltage drop of the diode, typically there is no employed diode here. Is employed another MOSFET. As you can see here, there is another N MOSFET, and this N MOSFET is driven by a signal which is the logical inverter signal that you can have for the switch A+. So now, instead of having just one active switch, the MOSFET, a controllable switch that you can command on and off, and the diode, which is a non-controllable switch, but it becomes on and off depending on the electrical characteristic of the circuits in which it is inserted. Now you have two controllable switches. When you want to have the principal, the main switch A+ on, you have to put this unity switching function QA to be 1. And then you have 1 here, switch A+ on. And then this is inverted by this logical NOT here. And so the switch function for the A- switch is 0, and this is off. When you want to, in the second part of the period, to switch off A+, you have to put QA 0, and then this logical inversion here put switch A- 1, so this is on. And this triangle here is the gate driver. It is a circuit that generates the correct voltage level and current level for driving the system. This is not the driver, this is the NOT gate. Okay, this is the NOT gate. NOT gate means that logically inversion is the operation. Okay, so you can command both of the switch in this way, and so they act exactly like the previous situation, which you have the switch and the diode. Which is the difference? The difference is that you should know mechatronics students, because they learned in the lectures about the devices, and electronic students from previous courses, that when the MOSFET is on, when a MOSFET is on, so when a channel is formed under the gate, what happens is that the current can flow from the source to the drain, but also from the drain to the source. Okay, so what happens when the switch A plus is off and the switch A minus is on? That the current through the inductor here want to flow in this direction. Okay, so if you want to the current flow in this direction and the MOSFET is on, this current can flow through the MOSFET, because typically power MOSFET have a on resistance that can be very low, and the voltage drop that is caused by this current flowing to the MOSFET is much lower than the voltage drop that you can have on a diode. Okay, even an order of magnitude less. So that means that you can have 0.5, then you can have, say, less than 50 millivolts, for example. Okay, so this is the reason why you can use this switch. Okay, when you put the switch on, it can act as a freewheeler for the inductor current. Okay, making the current flowing from the drain to the source and inducing a voltage drop across the MOSFET, which is let's say much smaller than that you can have. This typically happens because the construction of the power MOSFET generates a very small around resistance. Of course, you have to choose for that application specific MOSFET with very low on resistance that can be low as, let's say, a few million. Okay? And then if you can have a few million, then you can have very small voltage drop across it on average during TS. Okay? This kind of buck converter is called the synchronous buck converter. Okay? Synchronous because now the switch A plus and A minus can be, let's say, made open and closed depending on a signal, on the stereo signal. So they are both controllable switch, and they on and open conduction state are synchronized. Okay, when the switch A plus is off, A minus is on, and also the opposite happens. Okay, you can find typically this synchronous buck converter for operation at very low voltage at the output. Typically for driving, say, microprocessor or another application using very low voltage at the output. There are voltage levels that are compared with the voltage drop of standard power diodes. Okay, let's have a small break up to 10, 10:08, okay, and then we can continue. Okay, let's continue our discussion about the buck converter. Let me share the white screen in order to discuss the multiphase buck converter. Okay. I just said that in some application, it can be required to generate an output voltage which is very low, in the order of some few volts, for example, 1 volt or 1.5 volt. Typical application when you have microprocessor that should be supplied, I already said that in that specific situation, typically you have to change your configuration, replacing the diode, even a Schottky diode, with the synchronous buck converter, in which you use two switches, okay, that are commanded by, say, complementary signals, okay, in order to get one transistor on at a time. There are another consideration you can have for that kind of application is that the following. consider the output voltage V naught, and this output voltage, as I explained to you before, is imposed by a DC value, which is V naught, but then you have always a small ripple superimposed onto it, okay? For example, the ripple I discussed with you before, like this, or the more typical triangular waveform ripple that you can have. So this delta V naught, okay, the peak-to-peak ripple of the output voltage. So when you have V naught voltage, which is in the range of, let's say, 1 volt, of course, you also have to maintain this output voltage ripple, delta V naught, to value that are, say, well less 1 volt. So very small output ripple is required in all the applications which the output voltage is very low. Okay, this is quite easy to understand. But what does it mean to have a very low output peak-to-peak ripple? But this output ripple, delta VO, is something that is a residual effect of a non-ideal, non-perfect filtering action of the inductance and the capacitor on the output side of the converter. Okay, if ideally you have an say perfect filters, low-pass filters, in that kind of situation you cannot have any ripple because the constant voltage, the output voltage is constant. Okay, so it happens because your L and C are not a good filter. In order to have a very better filter reaction, you have to increase, okay, the value of the inductance and the output capacitance. For example, previously I derived an expression for delta VO that is useful for ceramic capacitances. Okay? And this expression is delta V naught, which depends on delta IL, which is 8 C naught multiplied Fs. Okay? So in that situation, you can have that here you have delta IL, but delta IL is V naught 1 minus D LFS. So if you want to have a very small delta V naught, you have to reduce delta IL, so you have to increase L, increase it, and then you have to increase C naught. Okay, so L and C naught should be very large. And this is my, say, drawback, because very large inductors and capacitance to the value that I need for reducing this, say, ripple to a fraction of very small output voltage, sometimes are not practical at all. Okay, large capacitance and inductance always bring with them large parasitics. And for example, if C0 is a electrolytic capacitance, it means that you can have a large ESR, but you have large ESR, then you have large delta V0, as I explained before. So there are several drawbacks in having this value too large. Okay? So we search for another means to reduce this delta V0 by using the same value of inductance and capacitance. And this is the multiphase buck converter. Multiphase buck converter means that we put in parallel the converters. Okay, suppose that you have, for example, 2 buck in parallel. Okay, in parallel means that I have one just single input voltage in, so one single input capacitance in, and then here I have not just one buck but 2 buck converters. One is here, and I put another switch here because typically here you can use that synchronous topology. And the output is common for the parallel converters. Okay, this is the switch 1, this is L1, this is the switch A, 1 minus, this is 1 plus. This is one converter. Okay, so this is the buck converter just I examined in this lecture. But then I put another one in parallel here. Watch the switch 2 plus, for example. Then I have an inductor L2, and then I have here another switch 2 minus. The two inductors have the same output, so they can merge into the same output node. And the two switches here have the same, connected to the same active node here. Okay. Then you have two switching nodes here that are different. Okay. So I put, in this case, n number of parallel converters, number 2. Okay, 2 converters. So what happens? How can you drive these two bucks? You can drive in this way. Let's have a look to the inductance voltage, VL1, for example, and VL2. VL1 and VL2, L1 and 2 are these two voltages. Supposing that this is my switching period, yes. Okay. The first phase is to put the switch S1, SW1 plus to be on. So if you have this duty cycle, for example, the inductance voltage is something like this. Okay. So in this interval here, the switch 1 plus is on. In this other interval, the switch 1 minus is on. So that means that you have here the classical V in minus V naught voltage, and here you can have minus V naught voltage. So look just at this VL1 wafer. Nothing changed with respect to the already known. Okay? The duty cycle now is T1 over Ts. What happens to the parallel, the converter which is put in parallel? The converter which is put in parallel is commanded to be on, not at time instant 0, like the switch 1 plus and 1 minus, but at Ts divided by 2. So at this point, you can have the same duty cycle. So the switching action for the parallel converter is shifted by, let's say, 180 degrees, if you want to look in degree and not in time, okay? Even 360 degrees the overall period, half the period, okay? So here you have the switch 2 plus on, and here you have switch 2 minus on. Also here, switch 2 minus. So the same duty cycle, the same T on period for both the converters, but then I shifted, let's say, the time instant in which you can get the T on. Okay, look at the current flowing through the inductors. You should know that when the voltage is V in minus V naught, the inductor current rise up with a specific slope, which is V in minus V naught divided by F. And then it decreases with negative V naught over L during T on. Okay, this is the inductor current IL1. What happens for the inductor current VL2? The same, but shifted by 180 degrees. Okay, this is IL2. Now, if you understand this construction, then you have to understand that IL1 and IL2 sum up at the node out. Then here the current exiting is IL1 plus IL2. Okay, this is the current which drives the output side of the converter. So let's have a look to the summation of the two currents. IL1 plus IL. If you look at the summation of these two currents, then you can have this is TS. Then you have first Tion. In Tion you have a rising edge for VL1, and then you have a falling edge, descending edge for VL2. But the slope of VL2 is less than the slope of VL1. So that means that you can have a rising edge, but a slope which is less, the difference between the two. Then you have a interval up to Ts divided by 2, in which you have both descending slope. So you have a descending slope here. Even less. Okay. Then you have Ts divided by 2 plus Tion is here, in which you have a descending slope for IL1 and a rising slope for IL2, but now the slope of the rising current is higher. You have a positive slope here, and then a negative slope here. So first of all, we can say that the output current has a switching frequency of the summation at IL1, IL2, which is 2 times Fs. So the switching is increased. The output ripple, as a consequence, is reduced. Delta IL1 plus 2 now is less than this delta IL2 or delta IL1. Delta IL1 plus 2 is less than delta IL1 or delta IL2. Okay. So in that situation, with the same inductance as before, we can get a ripple which is less. Okay, simply because you drive this circuit with an upper frequency which is 2 times the frequency you can get before. And so that means that, for example, delta L is less due to this. Okay, and also delta V, of course. What happens is, for example, the duty cycle is say 50%. Okay. If the duty cycle is 50%, then you can withdraw both of these voltages, so this for duty cycle 1F, and then you can have that the now my Tion is half a period. Tion is Ts divided by 2. And this is VL1. Okay? It's V in minus V naught, negative V naught. For VL2, you have the same, but remember that we have to shift by half the period. As half this is VLT. Okay, so they have both 50%, so there are a shift of 180 degrees. For the current has a slope here, but the same slope happens here. So the duty cycle is the same, so the positive slope is the same as the negative slope. Same happens here. Okay, this is IL2, this is IL1. So now, if you get the summation of IL1 plus IL2 at the output node here, since the slope are the same for both T on and T off, the output current is constant. Okay? You get the construction IL plus IL1 plus IL2 is so no ripple there is. Okay? You are able to say have no ripple at all. Okay? So this situation only happens when you have duty cycle 1. Since typically duty cycle is changing, then you can have say what happens here is that you can have a small ripple, but the ripple is present anyway. So this happens for two buck. Of course, you can easily understand that if you can increase the number of bucks that you put in parallel, then you can have situations that are even better. If you have, for example, generally n buck converted in parallel, then you have to shift the command of the subsequent converted not by Ts divided by 2, but Ts divided by n. Okay, so you have to shift by 360 degrees over n. Okay, if n is the number of parallel converters. The output frequency that you can have depends on n. For two converted in parallel, you have 2fs. In general, you have nfs if you have n converted. Okay? In that situation, the ripple is even lower. Okay? This is a possible solution for a situation in which you need very small ripple at the output. Okay? Questions about this consideration? This is all for continuous conduction mode of buck converter. Let's start a discussion about the discontinuous conduction mode of the buck converter. Okay? I have to say at the very beginning that typically buck converters are not operated in discontinuous conduction mode. So they are typically operated in continuous conduction mode. And this is due for the fact that, as we'll see in a few slides, then in discontinuous conduction mode, the stresses of components are typically higher. Okay, so this means that you have to choose large components, so more expensive. They have to say support more electrical stresses across it, so more higher RMS current, for example, higher peak current, and so this is not sometimes convenient, especially if you can have the same performances with the continuous conduction. So this is as a general consideration, but let's have a look anyway from this kind of operation, not to understand what happens, because other topologies, typically, for example, the boost, are only operated in discontinuous conduction. So important to understand. Also the nomenclature that is used for discontinuous. As I said at one of the lectures that we have last week, is that if you start your analysis in continuous conduction mode, you should understand that the average value of the inductor current is the I naught current, the output current. Okay? So the I naught current is the ratio between the output voltage V naught and the equivalent resistance R. So V naught over R. So I naught depends on the output resistance. If you increase the output resistance, so if you have less current, so you are going what is called a light load, If you have a light load, so increasing R, this I0 current is lower. What happens to the ripple, the peak-to-peak ripple of the output current, of the inductor current? This inductor current ripple is V0 divided L divided switching frequency multiplied 1 minus B. So it does not depend on the resistance, on the output load. So even if you change the output load R, the ripple delta L does not change, it's always the same. So what happens if you go into the situation which the load is light? So increasing the load means that you reducing I0, so this IL curve, so the current through the inductor, rigidly translates to lower value. Okay? And eventually it happens that, as it's shown in this second figure in the slide, the minimum current of the inductor touches zero, and then it becomes also lower than zero. It should become, it won't become lower, less than zero. In that situation, what happens? While in the continuous conduction mode, the maximum current, Imax, is well less the I0 current here. When the load current is very low, I0 is very low, then the maximum current is, let's say, comparable to the output current. So it means that you have exaggerated when, say, reducing the load. In that situation, you can enter in what is called the discontinuous conduction mode. Since this will always happen when your light is low, sometimes you can call also DCM or, say, light load mode, while the continuous conduction mode is called also heavy mode. Okay? So look, for example, at the inductor current and the diode current in continuous conduction mode. Okay? So as you can see here, the inductor current is never reaches zero. Then diode current is the same of the inductor current when the switch is off, so PNP off. This slide reports exactly what I said before. So the load current depends on load, the ripple current does not depend on load. So increasing R, it happens that first you meet what is called the boundary mode or the critical operating mode, in which you have that the current, the minimum current is zero. And this is the situation that's depicted here. As you can see for the diode current, in that situation, the current at the end of the S of the diode reaches exactly zero, okay, here. From this situation, which is the boundary situation between the continuous conduction mode and the discontinuous conduction mode, what happens if we increase the mode again? So we go into the light mode even worse, okay? It means that the minimum current should becomes negative, okay? So project this triangle away from here to negative value, okay? It wants to become negative. It means that the diode current should become negative, but current to the diode cannot become negative, cannot flow from the anode to, from the cathode to the anode. So in that situation, the diode becomes off. So if you look at this situation, which is the typical waveform description that you can have in discontinuous conduction mode for the buck converter, you can see that the inductor current is, say, zero for a certain part of the period. Even out, remember that the standard definition is that you have to look at the time derivative of the inductor current, but most of the time is the same of saying that the current inductor goes to zero to say that the buck is operated in. And in that interval, which is called T3, you can have the switch, which is off, because the switch is only on here during T1 or T1. From this point on, this interval, from TS, the switch is also, it's always off, okay? So the switch is off here. But what happens here is that also the diode is off. Because the diode cannot withstand a current flowing from the cathode to the anode. Okay, the current here, the inductor current should become negative, so the current from the inductor should reverse its direction, but the current in the opposite direction cannot be supported, cannot be conducted by the diode, which becomes off. So in discontinuous conduction mode, there is the time interval T1 or T on, okay, in which the switch is on and the diode is off, followed by the time interval T2, in which the switch is off and the diode is again off. Okay. Yeah. And then you have a time interval T3. Sometimes this is also called T idle, okay, in which both the switch and the diode are off. So as you can see, you can describe the discontinuous conduction mode by inserting a third state of conduction in which both the switch and the diode are off. Okay. Remember that in the beginning of the discussion, I said that the switch network can have two different states, but can accept a third one, which the switch are both off. Okay, this continuous conduction mode exploit this state of conduction with both the switch are off in this T idle or T3 interval. So the TS period is not only composed by T on, switch on, or T off, which is off, but then you have a third timing. Remember that we already derived the expression for getting the NVCM operation, so it can be described in terms of L, or the same in terms of R, if you have the inductance defined. But let's have a look at what does it mean in terms of circuit construction and topology. Okay, so in the time interval T1, sometimes I call this also T on. Okay, and on refers to the switch. Then you have this classical situation, already, say, known by CCM. Then in the time interval T2, then you have the situation which is reversed, which is off and diode on. Pay attention that now T2 is not T off, is not TS minus T on. Okay? So here you can have to understand that T2 is not TS minus T1. Because there is the time interval T3 or T idle, in which both the switch and the diode are off. Okay, so they are left open. So let's, and this requires the whiteboard, derive the conversion ratio for the buck in discontinuous conduction mode. DCM or light mode of the buck. Okay, and let's have a look to the voltage across the inductor. Okay, this is exactly what we did for deriving the conversion ratio M in CCM. Okay? We have to look to the DL. Now, the interval TS is composed of, let's say, T1, and we have another time interval which is Q, and then you have also T3. Okay? During T1, the inductor voltage is V in minus V off, because nothing changes in the space. During T2, you have negative T naught. And then what happens when we have T3? But when you have your buck in the T3 time interval, both the switch and the diode are off. Okay, so that means that if you look at the voltage across the inductor, voltage here, voltage across the inductor is left open. Okay, there is no connection here at this node, the node C. Okay, so that means that the voltage across the inductor is 0. And then the cycle restarts. Okay, so we have switch on, we have here the diode on, and we have both. Let's have a look just to understand better what happens in this DCM mode, what happens to the voltage across the diode. Okay, the voltage that I call VC, do not say be confused by VC. This is not a capacitance, this is a common node. Okay, so VC for me is the voltage across this. This node is also called the switching node, of the common node. So when we are in the first part of the interval T1, then the switch is closed, the diode is off. In that situation, we have V in. Then when the switch is closed during T2, we can assume that the voltage drop across it is 0. Then what happens when we are in the third interval, the T3 or T idle time interval? Both the switch and the diode are off, so the voltage across this voltage node here is due to what? But the voltage across the inductor is null in this phase, because I described it as a null voltage here. So that means that the voltage across the diode is exactly V naught. V naught, which is less than V in. Okay. So this is what happens here, V naught. Okay. Pay attention, this is something that you can see in the laboratory. The fact that you can have here a not constant voltage is, let's say, a theoretical consideration. In practice, and this is something that you can see in your lab, here you can have some ringing, some voltage oscillations at specific frequency. Why? Because you have to understand that in a situation when you use real components, that you have to face the fact that you have some parasitics. Okay? And for example, I just discussed with you the fact that inductance have a parasitic capacitance placed in parallel, which is due to the terminal capacitances, so the capacitance of the terminal leads, and the capacitance of the loops of conducting material that are adjacent one to the others. Okay, so you have a certain C terminal capacitance. Also, the inductor which is open, sorry, the diode which is open has capacitance across the heat, which is the depletion capacitance of an protected MOS diode, and also the switch has capacitance across it when they are open. So when all the switches are open, then you have to consider the fact that in that specific situation you have a resonator. The resonator is composed by C MOS, C diode, and C term in parallel, and the inductor which is composed, which is formed by the proper inductor of the backward. Okay, so in terms of the AC circuits, C circuit, the circuit that is valid, that holds for that kind of resonations here, for the kind of ringing, the V in voltage, which is constant, can be considered to a short circuit. The output voltage is a constant, which is considered a circuit. So just for AC, you can have this kind of circuits here. Okay, in which I put V in and V not to be 0 because I just looking about the AC circuits that holds when you have this range. Okay? So in that situation, you have inductor which is in parallel with some paracyclics. So this is a resonator. And the resonance is 1 over Q, Q, L, C, paracyclic. Okay? So in order to avoid this ringing, you have to dump out this oscillation. You have to insert some resistance. Okay? This resistance can be added somewhere in the circuit. Okay? And using this resistance, you are constructing a circuit which is called snubber circuits. Okay? The details about how you can design snubber circuit will be provided in the lab, because you have to design a snubber circuit to avoid this ringing, and this ringing is something that you can see in the lab. Okay. So, a part of this say practical consideration, let me discuss with you the derivation of the conversion ratio, MDCM. The conversion ratio is what happens about the V0 over V in. Okay? As I said before, we can start from the inductor voltage, because we know that there is the voltage per second low of the inductor in steady state. No DC voltage can happen across inductor in DC. Okay, so let me consider that in order to have no DC component in the voltage across the inductor, the area here, the two areas, should be the same. Okay, this is A1 and this is A2. Okay, as we previously did for the CCM. So the area A1 is V in minus V0 multiplied T1, which is the same as V0 multiplied T2. Let me just derive for a second the ratio between T2 over T1, because it will be useful later. T2 over T1 is V in minus V0 minus 1. And take there because it will be useful. So, M DCM, so V0 over V in is given from this expression is T1 over T1 plus T2. So this ratio in CCM leads to T1 over Ts, because in CCM there is no T3 time interval. So T1 plus T2 is Ts. Okay? So in CCM this leads to D, the duty cycle. Now this is not D. Okay? Because in DCM T1 plus T2 is less than Ts, because there is. Okay? So what does it mean? That since in DCM T1 plus T2 is less than Ts, MDCM is higher than MCCM, because the denominator is less in DCM with respect to DCM. This leads as a first consideration. Okay, if you want to consider this fact, the conversion ratio in DCM is higher. So the conversion ratio in DCM is higher means that for the same input voltage, the output voltage is higher. Okay, this is for sure. Let me elaborate a little bit in detail this expression, okay? And in order to do that, let me consider, for example, the inductor current, okay? The voltage of the across the inductor is here, and so we can get that for each of these voltage level, you can get slope. Okay, positive slope when the voltage is positive, negative slope when the current when the voltage is negative. So let me discuss a little bit the inductor current in this year. Inductor current is something that is like this. Positive with slope V in minus V0 over L during T1. Slope negative, and with slope negative V naught over L during the time interval T2, and then 0 when you are during the idle T3. And then the cycle repeats itself. Okay? Which is the average value? The average value you can have here, average value of inductor current is always the output current I know, because no average value of the current can flow to the output capacitance. So this is always happens. How can you compute this average value? So I can compute, I know, average value if you call the peak current Imax is the area of this triangle averaged over Ts. So you can have Imax multiply T1 plus T2, which is the base. Okay. I1 plus T2 is the base of this triangle, divided by 2. And then divided averaged over Ts. I naught is VO over R. And Imax can be derived simply because we know that during T1, for example, the slope is V in minus V naught over L. So Imax will be V in minus V naught over L, which is the slope, multiplied T1. Let me put this Imax inside this expression, so I can get V in minus V naught over L multiply T1, and this is Imax, multiply T1 plus T2 over 2 Ts, which is equal to V naught over R. Okay, so this is the same expression in which I use Imax expression. Now, remember that I have this expression here. And also remember that I have, if I use this expression here, and I, for example, let's have a look here. We can use this expression directly here. If I put V in over V naught minus 1, and then I have, say, this is T2 plus T1, and then I want to compute T2 divided T1 plus 1. So that means that I have to put 1 here. And so this expression is V in over V naught. And so from this expression I can say that V in over V naught is equal to T2 plus T1 over T1. Okay? It's the same as this one if you want. So T1 plus T2 is this expression here, T1 plus T2 is equal to V in over V naught multiplied T1. If you want, you can simply derive this one from this expression here. T1 over T2 is simply V over V naught multiplied T1. Okay. Whatever expression you can use, you should understand that this is true. So let me replace T1 plus T2 inside this expression. V minus V naught over L multiply T1. Then you can have V in over V naught multiply T1. Okay, this is VO using this view, you can get this one. So let me write you a more clear version. U L yes T1 and T1 square, and then you have V in over V naught equal to V naught over R. And from this expression you can get this one. Now MDCM is V naught over V in, 1 over say 1 over Ts, if you want, is the switching frequency. So let me rewrite this expression here, and suppose that I can multiply by Ts divided Ts. Okay, so I just multiply this expression by 1. If you get this multiplication here, what you get? First of all, we can say that we can extract. Let me draw by. Let me say discuss step by step. We can get. Let me derive here, for example, VO, and so we get V in times 1 divided to LTS. I just extract VO from this here, T1 square and then I have V in over VO, and but V in over VO is 1 over MDCM. VO over R. VO over R means that I can put VO and VO here, okay? Then I can have TS and TS can be eliminated. Then I have, sorry, it's better not to eliminate this one. We have two, so one. It would be helpful to have both T1, it's called TS. Okay, so T1 and then TS and TS give you TS square. T1 over TS square is a duty cycle. So I have TS, which is 2 over L. V in over V on is 1 over MDCM minus 1. Duty cycle square divided 1 over MDC equal 1 over R. We finally get 1 MDCM minus 1, 1 MDCM, and then I have equals to QL Fs divided R d square. Let me check. Okay, that's good. Okay, this is the expression from which I can derive the conversion ratio and DCM for that. Let me rewrite this expression in a more, say, usual form. Is this one, okay? I can multiply this parenthesis here with 1 over m dcm, and you can get 1 over m dcm squared minus 1 over m dcm minus 2lfs over r. Okay, this is the second order expression, equation from which we can derive 1 over m dcm equal to 1, and we have two solutions, 1 plus 8 LFS, which is 4 times the distribution of this constant here divided by 2. A classical solution of this second order equation. The solution which is good for this kind of observation is the plus solution. Okay, just the plus solution. The minus solution leads to something which is not correct. Okay, and inverting this expression, we can say that m Cm, which is V naught over V in for the discontinuous conduction mode, will be 2 over 1 plus 1 plus 8 L Fs r d squared. So, as you can see, this is not a duty cycle as happens in the CCM. It's a much more complicated expression. And it's not all a little bit more complicated, even to derive if you want. But it depends on several parameters, okay, which is not only the duty cycle. Okay? In CCM, it's just B. Now, this expression also depends on the load, depends on R. Okay? It's load-dependent expression. So, let me say this. Okay, this is the M conversion ratio, which is say the include both the CCM and DCM conversion, which is D when okay, the K parameter, remember, which is QLF over Fs previously defined, is higher than K critical, which is 1 minus B. And it becomes this expression, okay, which I inserted K here just because K is QLFSR, when K is less than K critical. Okay, so let me share again the whiteboard. Remember what I said at the description of the back. When you have K critical, is 1 minus D. This is something like this, okay? This is the cycle, which ranges from 0 to 1, and then you have 0 to 1 here, okay? Suppose that K is something in between, K, which is Q L Fs over R, is here. What happens that for a specific duty cycle, D star, before this specific duty cycle, it works in DCM, here. And for values that are higher than the star, it works in CCM. Okay? So if you look at the M curve with respect to the duty cycle, okay, if K is higher than 1, for example, here, if K is higher than 1, then you are always CCM. And if you are in CCM, M is equal to D. And equal to D means that you have a slope, which is 1 here. Okay? This happens for in CCM. K higher than 1. What happens if, for example, K is 1F? If K is 1F, then it means that this star is 1F. So for duty cycles that are less than 1F, you are in DCM. And for duty cycles that are higher than 1F, you are in CCM. CCM, you have M, which is D, and when you are in, say, DCM, so for the cycle less than 1F, you have a graphical representation of M DCM is Q over 1 plus 1 plus 8 LFS D square, which is given by this curve here. Okay, if you plot versus D for very specific LFS in the cycle, you get this expression. What happens if you get K, which is 1/4? K is 1/4, you can have something which is here. So you have a duty cycle, which is higher. Okay, here, duty cycle this starts now is, say, 3/4. And for that kind of duty cycle, you have here DCM before, and then CCM. If the duty cycle is less than this value, then you can reach a situation which you can work. And so this for, say, reducing K. The curve, linear curve is the CCM operation, and curves that are, say, rounded is the expression of them. Okay, so this is the reason why you get this graph of M versus D. So when K is exactly 0, then you, say, have almost M, which is almost 1, okay, for all the duty cycle except for duty cycle. And that situation means that VO is almost the same or of V in, okay. The discontinuous conduction mode characteristics intersects the CCM characteristic exactly at points that are at the boundary to critical mode. So this is the DCM. As you can see, there is a very little bit complicated expression for DCM. Typically, you can have higher value of the output voltage with respect to the same input voltage. But what is more important, that all the parameters that are, say, should be computed for DCM changes. Okay, for example, the output susceptibility is delta VO or delta V in. This is the duty cycle for the CCM converter. Now is a little bit more complicated expression, but is always the conversion. What happens to the small signal output resistance? For CCM, the small signal output resistance is 0 because there is no relationship that involves the output current in the output expression delta VO or delta IO. Here, this output resistance is not 0. Try to compute this output resistance, starting from this expression, okay, and then deriving VO from this expression, replacing R with VO over I, V0 over I0 like here, okay, and then try to take the derivative of this expression this way and find what happens, okay. It happens something that could be strange, okay. Look at the sign of the resistance that you can get. Okay? The gain is the slope of the previous curve, the curve here. If you get the slope here, for it should be something like this. If you get the slope for any duty cycle T, delta V0 over delta T, which is the slope of the curve for DCM mode, depends now on many parameters. And the same way, show that by computing it, that is the same of the I described here. Okay, so all the small signal parameters that I can compute now are changing, okay? Especially the output resistance is different. But all the parameters now depends on, let's say, duty cycle, resistance, switching frequency, inductance, etc. Compare these parameters with that I derived from the CCM computation. Now, this is the slide that shows you why typically the DCM is not the classical operating mode for buck converter. this is not the classical operating mode because of this reason. Start from the consideration that if you want to pass from CCM to DCM, you have to say reducing the output current, so increasing the resistance. Okay? So in that situation, if you are say decreasing the output current, what happens? That situation happens that you can go in DCM. So if you make some reasoning in this way, you can say that the stress of the component is not so important because the output current is very low, and so there is no interest in stresses in this way. So why don't use DCM? Yes, but typically it happens that when you want to operate DCM your converter, you want to get the same output current you can get in the CCM. So now if you compare the two situations, okay, so this is the inductor current in CCM buck, the red one, and in green is the DCM buck. If you compare the two inductor current for the same I0 current, what happens? Since the I0 current is the average value of the inductor current, it means that both the curves will have the same average value. Okay? But then if you want to use DCM with the same average, the same output current, with the same average inductor current, with that you can have in the CCM, then it's quite too easy to understand. Then the maximum current, instantaneous current you can get in the inductor current is very huge. It typically is twice the I0 current. This is due because the average current is the same. So in order to have the same average current in CCM and DCM, the peak current in DCM is much larger, almost 2 times the maximum current you can have in buck CCM. In the same way, the delta EL, so the peak-to-peak current ripple, is incredibly easy in, say, very large with respect that you can have in CCM. So in all the situations which you want to use, you want to have a specific output current, V naught over R at the output, so we get that specific output voltage, then the stress of all the components are, say, extremely large with respect to that you can have in CCM. The current peak is twice as much in CCM. The delta EL, so the stress in the component is large, and from delta EL it depends on the root square current, etc. So the capacitor can be larger with worse ESR, etc., etc. So it's something that is not so common to find out, but we are doing it. This example. Electrical stress is so huge for a component. It can be expensive, and also say, the lifetime of your component that the converter should be. But if you, let's say, understand the operation of the CCM, operating the same way, you can find out all the parameters you can to design a DCM buck converter. You can operate in the same way we did for the CCM. For example, just a few examples. The switch current. The switch current is the same of the inductor current when the switch is on. And the switch is on during T1, so during this time interval. So you can say that the switch current now has this behavior. Which is the expression of the current flowing to the input capacitance. But is the same of the switch current less the average value of the switch current. But the average value of the switch current is the input DC current. So you can get this expression here. So nothing different from that we learned in CCM. Okay, the same operating steps. For example, how can we compute the root mean square current of the switch? Okay, because it's important in terms of conduction losses. This is a triangle. Okay, so we can use the definition of the root mean square value. So we have to square it, then you have to mean it in a period, and then you get the square root. When you get, let me share the whiteboard just to give you this example. Okay? When you have the switch current, which is now this way. And this is Imax. I have to square it. So I switch square. And this means that I have something that is parabolic segment here. Imax square. This is T1. This is Ts. Then I have to get the average. I have to mean it over a period of Ts. And you should remember that there is an expression that gives us the area of this parabolic triangle, which is 1/3 of the rectangle area, so T1, multiplied Imax square. Okay, this is the area of that rectangle which encloses the parabolic triangle. 1/3 of this one, and then you can get over Ts. This is I switch root mean square value square. T1 over Ts is the duty cycle, so this is 1. The duty cycle Imax. So the root mean square value of the switch is Imax multiplied with value. Okay. What happens to, so you can apply the same reasoning we get previously. Okay. You have to recognize when you can apply the flat top approximation, separate solid waving typically, or when you can use, say, initialize in this way. For example, the root mean square value of the current in input current. You have to apply the quadratic Kirchhoff current law, exactly as we did for the CCM. Okay? So the root mean square value here, square value of the current, is the difference between the root mean square value of the switch current minus the DC value of the current. The DC value of the current is the average value of the switch current, IN, and so you can get this difference here. This switch root mean square value is already computed by the expression I just derived, and I switch average value is simply the average of this current here, but the average is simply the area of this triangle is 1f T1 over Ts multiplied Imax. So 1f duty cycle Imax. So you get that the root mean square value of the input current is expressed in this way. Depends on this square root. So again, you have to consider that that should be a maximum, okay, if you plot this way. This maximum happens for 0.767 of the duty cycle, 2 divided by 3. If your duty cycle encloses this duty cycle, so your operating point encloses this. Okay? The same for the, I don't know, the output node. This is inductance current. The output node current is simply the inductor current minus the DC component, which is I naught. So you can have this expression here. Okay. How you can get the root mean square value of this current? Now, in order to get the root mean square value of this current, you can use again the quadratic Kirchhoff current law, and it's given by this expression. Okay, you have the summation of these currents, and then you can know that the inductor current includes AC and DC. IC not current includes also AC on the IC, and the output current is on the DC. So you can get this expression. Okay. So this is nothing more than a little bit more complicated if you want to derive this expression for DCM. Okay. Try to work them out if you want, in order to understand which are the differences, and it can be a good exercise. So for me, the back steady state description is ended now. We can see each other next Monday. So please attention. Friday at 10, Professor Covetti is in charge for a half an hour and a half exercitation in design CCM back-converter. Friday afternoon, starting from 2:30 p.m., LED 5 laboratory for people who booked seats on the student spot. we can meet each other, so me, next Monday at 10. Okay, I now put on the website the scheduling for the next week lecture. Okay, if you have questions, of course, I'm here to answer these questions. Or maybe you can also write an email. Okay, let's just have a look what happens in the last slide of this block of slides. There are some I put here. I derived all the equation that you need for, say, both DCM and DCM equation for your components. The DCM equation needs to, let's say, mathematical derivation if you want. If you want to write down, you can work on them out. All these expressions for CCM have been derived in this slide. And then you have a design checklist that you have to consider when you design, say, all the converters, all for the buck, for the boost, for the buck boost. Okay, then all the required electrical quantities values that you need to design. Okay, so take in huge consideration this slide because you need for your practical working exercise and for examination. Okay, if you have no question, we can stop here and see you with me next Monday with the lecture of power electronics and the lab Friday. Okay? Bye.